I think this will make sense, but everybody knows this. It's apples and oranges. Which model is best. But I think if you started to kind of embrace this framework of what I'm suggesting here at an organization level, which again is going to give you, it's going to make you more efficient. It's going to allow you to get models out there faster and more timely. If you kind of embrace this concept, you're going to have to start thinking about ways to compare output in a smart way. And you have to think about it in a context, in my judgment, for the broader organization versus just analytics. So not just data scientists, not just the analytics group, but beyond that, right? Executives, middle managers, things like that, that are really going to have to be able to use their thinking caps, tap into that, and take a look at. So you can see here, if I showed you model A and B, in model A, we have a likelihood of selling a vehicle in 30 days. The performance is 87% AUC, which is area under the curve. And then you have model B, which is predicting sales price of a vehicle, and the performance is 4,200 MAE. These are technical things. MAE is just, mean absolute error. So the big takeaway here is the top one, model A, measures kind of a binary number, right? A binary classification. So the difference between it, we sold something, we didn't sell something. And then the bottom one is around a regression or a numeric value. So, you can imagine if the car value was really 10,000, I might be at 6,000. I might have guessed it was 6,000, or I might have guessed it was about 14,000 because of that 4,000 spread on the numeric. So clearly, these are not the same kind of model. So there is no comparison of which one is better. They're just completely different. But to a layperson, they may not understand that. And I think it's important to kind of drive at that a little bit and make sure that people understand. This one's a little bit different. You can see here, these are exactly the same. We've got the same model metric, AUC. It's pretty clear that there's one, model D is 88, which higher is better, 100 is perfect. So model C looks like it's doing worse. But how can we know for sure? And that's the part that a lot of organizations are missing, and they don't know how to keep their data science teams accountable or their AI accountable, and they end up getting themselves into real trouble. For example, in this case here, what data was used? Well, we already know it was the Amazing Auto data that we showed earlier. That's true, but was it the same data, right? Was it the same cut of the data? What if it wasn't? If it wasn't, that starts to showcase there could have been something special about that other subset of data that would give the model a performance of 88%. Whereas maybe the one that model C at 87% actually is the better model. It just didn't see that data that you trained model D on. So we do our best, and I think it's a best practice to not only make it reproducible for other data scientists, but also to make it clear to others so they can kind of start to understand how it is that these things come together. Again, the AI itself doesn't care, right? The machine learning models, it just doesn't care. You can give it whatever you want to give it. It's going to train on it. It's going to make a prediction. In that way, it's for as smart as everyone thinks this stuff is, it's really not smart. It just takes whatever you want and it just produces what it can. So there's all these different steps that need to be thought through and protected. And the protection is for the data scientists, also for the organization itself.